Welcome to this movie on statistical mechanics. My name is Jos Thijssen and I have made this movie for my students in advanced statistical mechanics at the Technical University in Delft in the Netherlands. This movie deals with the cluster expansion, which is a perturbative way to analyze the equation of state for a gas consisting of interacting particles. So it systematically improves on the ideal gas, which is of course a nice description for non-interacting particles, and it yields an equation of state which is formulated as an expansion of the pressure in terms of powers of the density, and that expansion is called the virial expansion. I hope you enjoy the movie. The equation of state gives us the relation between the pressure, the volume, the number of particles and the temperature. The best known equation of state is the ideal gas, and the ideal gas describes non-interacting particles. Its P times V is N kBT. If the particles interact, we need a different equation of state, and we have already seen an example of that, the van der Waals equation of state, which reads P plus AN squared, where N is the little n, it's the density, N over V. And this term represents the attractive interactions between the particles, and then we have V minus NB, and B is the excluded volume per particle. So there is a contribution due to the attraction of the particles, that's this part, and one due to repulsive core of the particles, that's this part. Although it can be argued that the form of the van der Waals equation is by all means reasonable, in the end it is a phenomenological equation, and the parameters A and B have to be found from experiments. The ideal gas equation of state can also be written in terms of the density N over V in this form, and this form is okay at low density, so when the molecules of the gas are far apart, we don't have any interaction, so then this will be a satisfactory description. The interactions between the particles become more and more important with increasing density, and therefore it makes sense to write the pressure as an expansion in terms of the density, where the lowest order term should coincide with the ideal gas equation of state, and we anticipate that there are higher orders of the density which represent the effect of the interactions. So we could then write P in the following form, N kBT, which is the ideal gas law, times 1, and then we have higher order corrections in terms of the density, and the coefficients AJ in front of these powers, they would then be determined by the interaction potential. And so what we try in this lecture, in this video, is to relate the interaction potential directly to these coefficients A1, A2, etc. Interestingly, the van der Waals equation of state can also be written as such an expansion. If we write P now in this form, so this is just a rewriting of the original van der Waals equation of state, and then we can expand the right hand side in terms of this N, and then we get for the first terms 1 plus NB minus AN over kBT plus N squared B squared, etc. Generally, the expression of P in terms of power series in N is called a virial expansion. And our aim, as said before, is to calculate these coefficients AJ in front of the n to the power j. In order to do this, we use perturbation theory, and in order to avoid complications, we take the simplest possible interaction, which is an interaction in which the total potential of particles placed at positions R1 up to Rn can be written as a sum of 2-point interactions. In reality, when two particles are close, the presence of a third particle may induce 3-point interactions. They usually make the analysis a lot more complicated, so we stick here to 2-point interactions. The question is then, what is the form of this V, this two-particle potential? We assume that we are dealing with scalar particles. Those are particles which do not have a dipole moment or a quadrupole moment, and then the potential only depends on the distance between the two particles. A very popular form is the LambertJones potential, which has a repulsive core where the potential goes up very steeply with the power 1 over r to the 12th, and for long distances the potential is dominated by the second term, that's a 1 over r to the 6th, that has a physical background, this power 6, because that's the form of the dispersion interaction, which is caused by induced dipole interaction between the two particles. The LambertJones potential has two parameters, epsilon and sigma. Epsilon is an energy scale, it sets the depth of the potential well, and the sigma is the distance from the origin where the potential goes through zero. This potential is unsuitable for perturbation theory because it shoots up to infinity, and it can therefore not be considered as a small correction. In the partition function, this potential only occurs in the Boltzmann factor e to the power minus beta v Lj, and therefore it makes sense to see whether perhaps this factor would be small. After all, if we get close to the origin, then the potential goes to plus infinity, and so this Boltzmann factor goes to 0, and that's small enough. So here is a picture of this factor. It's the green curve, and we see that it's indeed 0 when the potential shoots up. Then it reaches a reasonable maximum value, but it goes to 1, and that's undesirable in the context of a perturbation theory, because it means that pairs that are very far apart give a finite contribution to this Boltzmann factor. So this Boltzmann factor is not suitable for perturbation theory. So we try something else. We take that green curve from the previous graph and we shift it downward by subtracting a minus 1. In that case, the repulsive core gives me minus 1 over a short distance. Then it shoots up to about 1.7, and finally this factor e to the power minus beta v Lj r minus 1 decays to 0, so particles that are far apart will not feel it. And so this seems a very promising function to use in a perturbation expansion. This function has a name, it's called the Meyer function, and it's e to the power minus beta v Lj r minus 1. Let's consider the partition function, which is e to the power minus beta times the Hamiltonian, which consists of kinetic and potential energy, and we integrate the partition function over all the momenta and all the positions, and the prefactors are there because of quantum mechanical effects. So let's first integrate over the p as usual, noting that the part containing the kinetic energy is a Gaussian function. In Pj we can perform all those integrals, and it leads to the thermal wavelength in the denominator here. Part of that is due to the h, and so we are left here with the so-called configuration integral Qntv, and that's the object that we want to analyze. In this integral we have an integrand which has the form e to the power minus beta times the sum over j smaller than k. So those are the pairs of particles. Each pair counts only once. And then we have here the LambertJones interaction. And for a sum in the exponent, we can also write a product in front of the exponent. So we can write this as a product over all the distinct pairs, and then the Boltzmann factor for each. So then we can indeed use this function fjk, which is the Boltzmann factor minus 1, provided we add 1 to it in the product. So instead of this term, we just add 1 and we subtract 1, and then we call this part, it's the well-known function fjk that we have met before, and so we have a product of factors 1 plus that function. And to remind you, that function was the function we were using in the perturbation expansion. It's this green function. Now recall that in order to obtain the configuration integral, we also need to integrate over all the r's. So we take this product and then we need to integrate over r's. I've done that here, so there is the integral over all the particle positions, and I have expanded this product for each pair explicitly. So for each pair we have a term 1 plus f of that pair. And then we can work out this product. And the simplest term is when we take a 1 everywhere. 1 times 1 times 1, etc. gives me a 1. I can also take a 1 everywhere except for one of the pairs. So in one of the pairs I take, for example, f3, 4, but for the remaining terms I take a 1. That results in a sum over all the possible pairs fjk. Then I can also take two pairs from these, and I should take each combination of two distinct pairs only once, and that's why I've put a primed with the sum. So the sum is over the pairs jk and the pairs lm. First of all, these pairs should not be identical, and second of all, they should occur only in one particular order and not, for example, 3, 4, 10, 20, and then again 10, 20, 3, 4. That combination should occur only once, and the same restriction holds then for the terms where I have 3 fk's. Everything should be counted only once. Every unique combination should be counted only once. Now we can identify each term in this expansion by a diagram, and that's rather straightforward. A function fjk connects 2 points j and k, and so it's natural to use the following diagrams. The fjk is just a line, and that line connects the points j and k. Then we have, for example, the term with fjk and flm. Those are two lines connecting the two different pairs of points j and k, l and m. But we can also have fjk, fkl, where the two lines share a vertex k, and then you have this diagram. And then here are the three lines which are completely separate, distinct pairs. Here are three lines which two of which share one vertex, and then of course we can also have a combination of three lines which form a triangle like this. So each fjk is identified with a line in the diagram. In this table I've listed on in the left column some of the simplest diagrams. The first one is a line connecting 2 points, so that corresponds to a pair of two particles. And if I have n particles, I can take the first one in n ways, and I can choose the second one then in n-1 ways, but I could also pick them in the reverse order. So I'm counting this diagram double, and I compensate for that by dividing by a factor of 2. So the multiplicity of this diagram, that's the number of ways in which I can realize it, is n times n minus 1 over 2. This diagram contributes to the configuration integral. It's through this term. It should be fjk d3rj d3rk, but I've just called the two coordinates here r1 and r2. And I can carry out this integral as follows. I can first take the integral over r1, and then I choose as a second new coordinate within the integral r2 minus r1, and I call that r. And then the f12 only depends on r, not on r1. So when I calculate the integral over r1, it gives me just a factor of v, because I integrate over the space in which the particles are moving. And the integral of f, which only depends on r, is listed here. And then I've defined here a new quantity that's b2, that's a coefficient. And this expression here is just 2 times v times b2. I will later on give a general definition of these coefficients, but for now it's just a simple definition of b2. Then we carry on with the second diagram, which consists of two lines. and I can take the first pair here in n times n minus 1 over 2 ways. Then two particles have been removed, so the second pair can be taken in n minus 2 times n minus 3 over 2 ways. And then I could of course take this pair first and then that pair, or the other way around, and that gives me an extra factor of a half, because otherwise I would be overcounting. The corresponding expression in the configuration integral is f(1,2), f(3,4). 1, 2, 3 and 4 are each distinct positions, because I have here 4 distinct points. And it's obvious that I can carry out the integral over dr1 and dr2 separately from the integral over dr3 and dr4, and both integrals give me the same result as this integral, but now I have it squared, and so the result is 4 times v squared times b squared, b2 squared. So all in all I have this multiplicity times 4 times v squared, b2 squared. The next diagram has 3 points connected by 2 lines. I can choose this in n times n minus 1 times n minus 2 over 3 factorial ways. Those are the possible orders in which I could have selected those points. And I have to multiply by 3. Why? Well, I'm looking at all the diagrams that I can make of this form, so I can either take this one to be the open link, not connected, or that one, or that one. So I can also look at those diagrams, this one and this one, and that gives me then, together with this one, the extra factor of 3 here. Calculating the expression corresponding to this, I have an f(1,2) times f(2,3), where I have numbered the vertices in this way. So I have f(1,2) and f(2,3), and I have to integrate over all 3 coordinates. But I can, just like I did in the previous case, I can use new variables. So I have the f2, I integrate over f2, which means that I take this cluster and it can be moved all over the volume. And then the only thing which counts in the integrand is the distance between 2 and 1 and the distance between 2 and 3. And they occur in these f factors, f(1,2) and f(2,3). And if you then look at this integral and you compare it with this one, it's exactly the same, because I have an integral over r(2,1), which is completely decoupled from the other part. So that gives me a factor like I have here. And then I have an integral over the r(2,3), which is also decoupled, and it gives me another such factor. So in total I have 4 times v times b squared. Now the difference with the previous term is that the v occurs now linearly, whereas here it occurred squared. And that's because I can pick this up, move it through the entire volume. I can pick this one up and move it through the entire volume, so I have a v squared. However, this angle here, it can be picked up and moved over the entire volume, and that's it. So I have only one volume integral. Finally, I consider the closed triangle, which has 3 vertices, which I have labeled in the same way as in this diagram. I can make the triangle in n times n minus 1, n minus 2 over 3 factorial ways, and there is no factor 3 here, because the factor 3 came because I could in fact have 3 diagrams. I could have the the point connecting the 2 others could be this one, that one, or that one, as we have seen before. That's not possible here. There is only a single diagram. The contribution to the configuration integral is listed here, and it contains, of course, the 2 lines which I have here. I'm going to use the same new coordinates within the integral as I did here, r2, r2,1 and r2,3. And so the question which pops up then is, what about r1,3? Well, r1,3 is r2,3 minus r2,1, And so I can express this in terms of the coordinates r1, 2, 1 and r2, 3. So I just have these three in one integral, and I call that integral 3 factorial v times b3 minus b2 squared. So we will see later why I have these strange definitions with here a 3 factorial and here the b3. The b2 is the same one as I had there. But anyhow, this is just considered to be a definition of b3. You can view it as a definition of that quantity. So I can collect all these terms and construct a series of for Qn, the configuration integral. And to remind you, what we are doing is we are evaluating this expression. The first term consisted of taking a 1 in each term here, and that gives you a 1 here. When I integrate over the r's, it gives me a v to the power n. So the first term is v to the power n, and I've symbolically represented that as a single dot. In fact, these should be n dots because I have n particles. Each of these particles is integrated over. Now we consider the term corresponding to the diagram consisting of 2 points connected by a line. It's this diagram here. So there should be a factor of n times n minus 1, and the factor itself contains a factor of v. In fact, the remaining points, those are v times n to the power minus 2. And then together with the v, which I have here, I should have an v to the power n minus 1. And that's what I have here. I've written a v to the power n in front of each term, and then I divide by v, so this is v to the power n minus 1. Then I had n times n minus 1 over 2, and that 2 in the denominator is compensated by the 2 from the definition here involving the b2. Then I move on to the next term. That is the term corresponding to 2 lines, 2 pairs. We have seen that this can be realized in n times n minus 1 times n minus 2, n minus 3 over 8 ways. So you see that occurring here. Outside of these 4 points, we have v to the power n minus 4, and then the expression here contributes another factor of v squared. So the net factor of v is v to the power n minus 2. So that's why I've put a v squared here in the denominator. And then there was a 4b2 squared. Then we move on to the next term. That is this diagram, which we can still see here. And this is the prefactor that we had, and we multiply that by 4 for vb2 squared. And for the triangle, we can do the similar procedure, and this is what we end up with. Terms in the expansion. And, well, I say expansion, but obviously it looks a bit strange because we have an expansion in terms which we can be sure are not small, because this is n squared over v. Here we have n to the 4th over v squared, and here n to the 3rd over v squared. Nevertheless, we are dealing with the configuration integral, and we still need to take the logarithm, and it turns out when you take the logarithm, then all the bad terms, they cancel out. But we will proceed in a somewhat different way. So what do we finally have? We have an expression for the partition function, where I have restored the thermal wavelength and the n factorial, so that we have here the part which arises from the configuration integral. And the configuration integral is a sum over all the possible diagrams, so those are all the possible ways in which I can draw lines between points, point pairs, FKL. And for each such diagram, I have the product of all the drawn lines, which occurs here in the integral, and then I need to integrate over the d3 and r. Now, in order to streamline this expression a bit, let's consider all the connected diagrams for j sites. So I take j points from my system. In this case, I have 1, 2, 3, 4, 5 points. And I consider all the possible ways in which I connect all these 5 points. So this is a not connected diagram. This is a connected diagram. I can also connect it like this. I can draw lines between all the possible points, and all these diagrams have to be summed over in the sum which is here, which is a sum over all the connected diagrams. And for each diagram, of course I have different diagrams, so I have a variable number of links, and for each link I write down this vector FLK. I integrate over all the points within the diagram, and I call that j factorial v times bj. And this is the bj that we have seen already before. Here we have seen the b2 and the b3. And so this is the general definition for the bj. And the b1 is by definition just 1. So let us check this definition for the 2 points. Then we have just one line connecting the 2 points. We need to connect them because otherwise we don't have a connected diagram. And we had seen that this gave rise to this expression. This is integral v times the integral of f. And by definition we have then a 2 factorial, which is 2 times v times b2, and that matches precisely the definition we have used above. Next we consider the closed diagrams on 3 points. There were 3 open angles and there was a closed triangle, 4 in total. For the open angles we have 2 lines. Each line has its own integral over the Meyer function, so that occurs with a square, a factor 3 because we have 3 of those, and then a v because we can pick up this vertex and move it over space. And then for the triangle we can also pick up one vertex and move it over space. And then we have the internal lines f1, f2, and then we have f1, 2. So this is a shorthand notation for the integral. And we had seen before that this one gave me a 2b2. That's also still visible here. And this diagram was defined as b3 minus 2b2 squared with a 3 factorial v. And if we put everything together, we see that we indeed end up with a 3 factorial v times b3, which matches this formula for the 3 vertices. Now for the partition function we need to sum over all possible clusters, and we can do that by in a particular way. So when we make a cluster we take all the endpoints, and first of all we partition them into clusters, and the clusters will be connected by connected diagrams. So the cluster size is j, and for each j we have mj clusters of that size. And then per cluster we have a factor that we have just studied before that gave me a j factorial v times bj. And as we have mj clusters of size j, we raise that to the power mj. And then we turn to the multiplicity. First of all, obviously if we change in the order of the points, then in principle we could get a different cluster. So we put an n factorial here. However, that is overcounting, because if we change the points within a cluster, that's this j factorial, we can reorder the points within a cluster in j factorial ways. And so that doesn't change the clustering. So that's why we have here a j factorial in the denominator, and because we have mj clusters, we have this j factorial to the power mj. Furthermore, there are mj clusters indeed, and if I swap those clusters, and I can order those clusters in mj ways, we have this factor mj factorial. in the denominator, and that completes the expression for the partition function. May be useful to illustrate this expression using a picture. Here we have the n points. They are labeled from 1 to n. And the first step consists of partitioning these points into clusters. So we identify certain points to be part of the same cluster, like these 4 here. Here we have a cluster of size 2, and there we have a cluster of size 2. Then, of course, we are left with some isolated points. They are considered to be clusters of size 1. So in the end, in this case, we have 1, 2, 3, 4 clusters of size 1. We have 2 clusters of size 2. We have 1 cluster of size 4, which means that in this case mj, m1 is 4, m2 is 2, and m4 is 1. And now to consider this multiplicity factor again. We can, of course, link this 4 cluster in different ways. We could, for example, add this line here, or we could add a line between these two and then perhaps leave out this line. But they should, of course, be connected, but then that can be done in different ways, and that's all contained in this factor. Now, if we reorder the points, then in principle we could get a different cluster, and that's accounted for by this factor of n factorial. But of course, not each reordering of the points gives rise to a reordering of the cluster. For example, if we permute only these 2 points, then obviously nothing changes, because permuting the points within a cluster gives us the same cluster diagram as before. So this accounts for reordering the points within a cluster. A cluster has size j, and so there are j factorial reorderings, and I have mj clusters, so I should compensate by a factor j factorial to the power mj. However, I could also swap these 2 points with these 2 points, which means that I swap the 2 clusters. And that is a direct consequence of the fact that I have 2 clusters of size 2. And that also is a redundancy that I have to remove, and therefore there is a factor of mj factorial. I have 2 clusters, and the ways in which I can reorder them occurs here. For the 1 clusters I would have a 4 factorial here. Here I've copied the expression for the partition function, and we see immediately that the 2n factorials cancel to give a 1. And what I would like to do now is evaluate this expression. However, there is a constraint to which all these mj's and j's should be subject. And that constraint is that j times mj summed over j, where j runs from 1 to n, should be n, because that's the total number of particles, and I have j clusters each of size mj. And it's particular this constraint which makes it very difficult to evaluate this expression. And so it would be very convenient if we could relax this constraint, and that can be done indeed, but only by going to the grand canonical ensemble. So we now give up the canonical ensemble, we go to the grand canonical ensemble, because that does not impose a limit on the number of particles. In that sense, this step is very similar to what we do in quantum statistics, where we also go to the grand canonical ensemble in the case of non-interacting particles, also for interacting particles, because it's difficult to handle the constraint on the particle. So the sum over all the partitionings, which we have carried out so far as a sum of all the partitionings mj which are subject to this constraint, sum over j times mj is n, is now replaced by this expression. So for each cluster size, we have a number of clusters ranging from 0 to infinity, and we just take this product and we have all possible combinations of partitionings of arbitrary numbers of particles. This way we generate all particular configurations j and mj, and if we want to know what for this particular configuration is the number of particles, then that is still, of course, equal to the sum over j times nj. That's not constrained, but for each configuration which occurs here in this product sum combination, we can evaluate how many particles there are in total in the system for that particular configuration, for that partitioning. If we write up the grand canonical partition function, it has this form. There is this factor of e to the power beta mu n, and then for one of those n, if we fix n, we have here the previous expression for the partition function, and that contains also an n here with the thermal wavelength. So we have the sum over we have here this expression which only depends on the partitioning. And then we have here a factor n, and there we have a factor n. So we are going to replace this by a different sum. Here is my new expression, which is a sum over all possible partitionings with an unrestricted particle number. Then there is here the old factor that I had before, and this term is new, and it's in fact it derives from the e to the power beta mu and the lambda t to the third, which are raised to the power n, and I use the fact that the sum over j times mj is equal to n. So, and the product over the j here will be a sum in the exponent, and therefore this is the correct expression for the grand canonical partition function. So if I move this term under the parenthesis here, I obtain this expression. Furthermore, I see that the j factorial raised to the power mj in the numerator is compensated against the identical term in the denominator. And if I then consider a sum over mj 0 to infinity with 1 over mj factorial times something raised to the power mj, that's the exponential function of this quantity. So I can now write up immediately the grand canonical partition function in terms of a product over j running from 1 to infinity. And this is the result. It's the product for j running from 1 to infinity of the exponent of this factor here, which contains a bj and here also a j, so it's dependent on j. And to obtain the equation of state, we take the logarithm of the partition function of the grand canonical partition function, and that follows directly from this expression where I have called the expression in the parentheses here xi. It's just a shorthand notation. And then we know that kbt times ln z grand is p times v. So we have now found p times v as an expansion, as a power series in terms of this parameter xi. So here is the expansion of p in terms of xi. The coefficients are just the bj, and we have used here the factor the b1 is 1. And the xi is this fugacity divided by the thermal wavelength raised to the power 3. However, this is not really what we want, because the aim was to obtain b as an expansion in terms of n, the density, and not in terms of the xi. So we need to address the density, which can be obtained from the grand canonical partition function by taking the derivative with respect to the quantity beta mu. And if we do that, then we can use a chain rule. It's these ln z grand dxi, and then dxi d mu, which is nothing but xi itself. And so then we find the following. Recalling the expression for ln z grand, which is a simple power series in terms of xi, we immediately find that the density is given as a sum also in terms of the xi. So we have a power series in xi, which gives us the n, in addition to the power series that we have for p in terms of xi. And so that enables us to write p now in terms of a power series in n. So the idea is now the following. We have n as a power series in terms of the xi. Then imagine we can invert that expression so that we get xi as a power series in terms of n. Then we take that power series and substitute it for all the xi's occurring in the power series for p, and that will then give a power series in terms of n, and that is the final result we want to achieve. So we will carry out that procedure now up to order 3. We proceed order by order. The lowest order is very simple, because if we keep only the lowest order terms on the left and right hand side, we just have n is xi. So we have n is equal to xi plus corrections of order xi squared, and therefore xi to order 1 is n, which means that xi can be written as n plus terms of order n squared. Then we go to second order. And in second order, this equation is n is xi plus 2b2 xi squared. Both terms contain a factor of xi, which I can extract from the parentheses, and so this is the form, which is easy to invert. I write xi as n divided by this factor, so I divide on the left hand side by this factor, and then I Taylor expand that factor. And the first order Taylor expanded term is of order n squared. All the remaining terms are of higher order, and so I find that xi can be written as n minus 2 by b2 n squared plus order n to the third. Recall that the order of n is the same as the order of xi, which we know from the first order. And so we write now xi2 as xi to second order and then truncated, so we leave out all these n to the third terms. So then we move to the third order. We expand n to third ordering xi, and then we can extract xi from the parentheses. So that means that we can invert the equation as follows: xi is equal to n, and then we divide this by 1 plus 2b2 xi plus b3 xi squared. Then we can expand this to second order in the Taylor expansion, and then we have first n minus this term, and then this is the second order term, and I take only the lowest order correction into account, because this would give higher order corrections there. Then we proceed by plugging in for xi the expressions in terms of n that we have found before. So this is multiplied by n, so it's sufficient if we worked up to third order to put in the second order expansion for xi in terms of n. That's what we have done here. And for a term n times xi squared, it's even sufficient to put in only the lowest order, which gives me an n to the third. Obviously, higher order corrections can be neglected here. And then also for this, I take the lowest ordering xi, and then putting everything together, I have this expression for xi to third order in n. We see that it's the first two terms are obviously identical to what we found at the lower levels, and this is the third order correction, with this as the result if we neglect the higher order terms. So it is then immediately clear that if we want to find p to third order, it was given as xi plus b2 xi squared plus b3 xi to the third. We need to take the third order accurate expansion here, the second order accurate expansion there, then we have everything correct even to fourth order, and only the first order is required here. So that's what we are going to substitute now, the xi's to several orders expanded. So this is the result. Xi3 is these terms on the first line. Then here we have the term with xi at level 2 squared, and this is the first order approximation to xi to the power 3. And plugging everything together, we have then the third order expansion for p in terms of n. So one extra step consists of working out here the square. We can neglect the term n to the fourth, so I have only two terms from this, and those are these two. And then this is the final result for p. And this, therefore, is the virial expansion that we have derived. Now the aim of the calculation was to relate the interaction between the particles to the expansion coefficients, and those are given here in terms of the B's. Now recall that the definition of the B's was given in the terms of sums of connected diagrams, and then we have integrals over the FLK, and what was the function f? FLK is e to the power beta with a minus sign, V LambertJones, or whatever potential you would like to use, RLK minus 1. And so we see that here we have the potential going into the FLKs, then we calculate this integral, then the information has gone into the B's, and the B's enter then into the expansion coefficients of P in terms of n, and therefore in the equation of state. So that closes the circle. So what about the van der Waals equation of state? That had this form, and we can expand that also in terms of n, as we have done at the start of this movie. And so we have a term which is linear in n, and we have a term which is squared in n. And it's interesting to see what these terms would derive from in the cluster expansion. If we compare this expansion with the cluster expansion, we see that the term with n squared, that should, according to this expression, be minus b2. So b2 should be minus b plus a over kbt. And so let's see how b2 is calculated for the LambertJones potential. According to the definition of b2, this is given as 1/2 times the Meyer function, which is e to the power minus beta VLJ, depending on r, minus 1. And if we inspect the Meyer function once again for the LambertJones potential, we see that it's minus 1 up to the kind of cutoff radius. So this is the excluded volume. It corresponds to this area where the Meyer function is minus 1, because the Boltzmann factor is 0 there. And so, first of all, we have then, because of the minus 1, minus 1/2 times the excluded volume term, and then there is an extra term if we take we assume that the potential is weak, or equivalently that the temperature is high so that the beta is small. Then we can do a first order Taylor expansion of the exponent. We subtract the minus 1 and we are left with the following term, 1/2 times the integral over beta times VLJ. And therefore we see indeed that we have a term which is independent of the temperature, which is related to the excluded volume, that's B, and then the second term is the term which is the integral over the attractive part of the LambertJones potential, because this is only the part beyond the cutoff, where the cutoff, well, it's in fact beyond sigma, which is the point where the potential hits 0. And so we see that we can relate in this way the LambertJones potential very nicely to the coefficients occurring in the van der Waals equation. It turns out that if you look at the higher order terms in the van der Waals equation, that they all deviate a little bit from the cluster expansion, and that is because the van der Waals theory is a phenomenological theory. It's a mean field type of theory, and such theories, they never take all the diagrams into account. In fact, from the infinite series of diagrams, they take an infinite subset. So there are diagrams in this expansion. The expansion obviously goes up to arbitrary orders, but it doesn't take all the diagrams at each order into account. And so that concludes the discussion of the cluster expansion. And what we have seen is that we can start from an interaction potential between particles. We calculate for those the coefficients Bj via the Meyer function, and these Bj then end up in an expansion of the pressure in terms of the density, And that is the equation of state that we want to find.